Hey guys, and welcome today to where we're going to walk through the AS Core Pure paper for June 2019, or I think it was actually set in May. So this is the AS paper, so if you're looking for A2, I have walked through the Core Pure 1 and Core Pure 2 papers, so be sure to check them out. So this paper was pretty challenging overall. I'd say there was definitely some tricky questions in it, but the first few questions are quite a nice introduction to the paper. So let's take a look at these. So question 1 is a question regarding matrices. So we've got part A here, where we have to show that the matrix M is non-singular. So part A. So remember, if a matrix is non-singular, what that means is that the determinant, so the determinant of M in this case, is non-zero, so it's not equal to 0. So non-singular, this means the determinant of M, we have to show that it's not equal to 0. Okay, so it's a 2 by 2 matrix. All we've got to do is calculate the determinant, and for a 2 by 2 matrix, remember, say if your matrix is A, B, C, D, the determinant of this is A, D, so it's A times D minus B times C, okay, for the determinant. So if we do that with ours, it's going to be 4 times minus 7, so 4 lots of minus 7 minus, so we've got 2 times minus 5. So if I do minus, I'll do it in a bracket, 2 lots of minus 5. Okay, so doing this now, this is going to be minus 28. This would be minus 2 times minus 5, so that would be minus 10 minus minus 10. That's the same as add 10. So minus 28 plus 10 gives us minus 18. Okay, so because this is the determinant of M, so det M is equal to minus 18, so therefore M is non-singular, because we've shown that the determinant is not equal to 0. And there we have it. So that's part A. Part B now. So we're told that the transformation T of the plane is represented by the matrix M. Okay, so just the matrix that we started with. The triangle R is transformed to the triangle S by the transformation T, and we're given that the area of S is 63 square units. So we've now got to find the area of R. So 2 marks, so we should imagine that there's nothing too crazy with this. We've just got to be aware of the fact of the area scale factor for determinants, okay? So in this case here now, what this is saying is that the area of S, so the area of S, well, that's going to be equal to the absolute of the determinant of M times the area of R. Okay, so the area of R. Well, the area of S, we know that's 63 square units. We just want the area of R. So if we rearrange this, we can get the area of R. So therefore, in this case now, area of R, well, that'll just simply be the area of S divided by the determinant here, the absolute of the determinant. So area of S divided by the absolute of the determinant. Like so. Well, the area of S we got given, that's 63 square units, so 63 divided by the absolute of the determinant, so the absolute of minus 18. So now you can divide top and bottom by 9, so that's going to give me 7 over 2 square units. And there we go. So the area of R would be 7 over 2 square units. Okay, so that's part B. And then finally, for part C, we just have to show that the line y equals 2x is invariant under the transformation T. So remember that an invariant line of a transformation, that would be one where every point on the line is mapped to a point on the line, okay, on that same line. So what we've got here is y equals 2x, so part C, y equals 2x. So we could write this as a matrix. This would be, normally this would be x, y, right, if we had the form y equals mx plus c. But we've got our m would be 2 and our c is just going to be 0. So plugging this now in here using this equation, well, this is going to be x again, okay, because we've got our x here, and our y is equal to 2 lots of x. So where the y is, that's 2 lots of x. Okay, and now all we've got to do is multiply this with the matrix M here for the transformation. So doing that now, what we should get is we should get another invariant point. So what that be would be, for example, like 3x and 6x. Okay, so that would be 3x, that would be 6x, for example. That might be 2x, that would be 4x. Example, you know, it should always double the y here. So, or the y should always be double the x. So if we do that now, that's going to be 4 minus 5, 2 minus 7. Okay, and then multiply it by this, x, 2x. So doing this now, I'm going to get 4 times x, that's 4x, minus 5 times 2x, that's going to be minus 10x. Okay, so multiplying that row here by that column, and then finally we're going to do this row by this column, so 2 times x, 2x, and then minus 7 times 2x, that'd be minus 14x. Okay, so now let's calculate this. 4x minus 10x, that would be minus 6x, and 2x minus 14x, that'll be minus 12x. Okay, so this is good here. We've shown, or we've not shown just yet, we need to mention a little comment, but we've got the idea now that this here, or this point here, is 2 lots of this here. So all I'm going to do now is plot this factor of minus 6. So if I plot that factor of minus 6, I'm going to end up with x and 2x. Okay, so minus 6 lots of x and 2x, like so. So therefore, because we've got this x and 2x again, it must be y equals 2x must be invariant. Y equals 2x is invariant. And there we have it. So we've shown that the line y equals 2x is invariant under the transformation T. So moving on to question 2 now, we have a question here dealing with polynomials. So in this case we have a cubic equation, and we're given the roots alpha, beta and gamma, and we're asked, without solving the equation, to find the cubic equation whose roots are alpha plus 3, beta plus 3 and gamma plus 3. Okay, and we've got to find these 4 values here, p, q, r and s, where they're integers to be found. So there's a few different ways you can actually solve this. I think the easiest way would be to use substitution for this. Okay, so because we're in terms of w here, what I'm going to say, and because my roots are alpha plus 3, beta plus 3 and gamma plus 3, what I want is that w is equal to x plus 3. Okay, but what I'm going to do here is rearrange this now to be in terms of x. Okay, so we're going to make that connection between x and w. So therefore, x, nice and easy, should be equal to w minus 3. W minus 3. And now, all I've got to do is substitute this x here into my cubic here. Okay, and then doing that, we can get this new cubic polynomial here, this cubic equation. So doing that now, I've got 2 lots of x cubed, where x is w minus 3. So I'll just write all out first. 2 lots of w minus 3, all cubed, plus 6 lots of w minus 3 squared, minus 3 lots of w minus 3, plus 12. And this is equal to 0. Okay, so now we're going to have to start performing, you know, my cubed expression here, my squared expression, and then just simplify everything. So to perform this, what I'm going to do is I'm just going to write out what w minus 3 squared will be first. So I'll just be w minus 3 squared. Well, that'll be equal to w squared minus 6w plus 9. Okay, so that's that part there. And if I want the cubic here now, so to times it by w minus 3 again, times w squared minus 6w plus 9. Okay, so I can expand across this, so it'd be w times this, this and this, and then minus 3 times this, this and this. So let's start doing that, right? So this is going to be quite long. Hopefully I will have just about enough room. So this is going to be 2 lots now of, so that'll be w times w squared, so that'll be w cubed. Okay, w times minus 6w, so that'll be minus 6w squared. W times 9, so that'll be plus 9w. Okay, so that's all good so far. I'm going to get minus 3 times w squared, so that'll be minus 3w squared. Minus 3 times minus 6w, so that'll be plus 18w. And then minus 3 times 9, that'll be minus 27. Okay, so all of that will be times by 2, because that's 2 lots of x cubed. We've got 6 lots of this, so this is going to be running off the page here. So let's see if we can fit most of it on. So 6 lots of this, so 6 lots of w squared minus 6w plus 9, minus 3 lots of this, so minus 3 times w, so minus 3w, and then minus 3 times minus 3 plus 9. And we've got our plus 12 at the end, and this is equal to 0. So it's quite long, but let's carry on simplifying this. So now I'm just going to expand everything in here by 2. So 2 times everything, so I'm going to get 2w cubed minus 12w squared plus 18w minus 6w squared plus 18w minus 27. Times in this through by 6 now, so I'm going to get plus 6w squared minus 36w. 6 times 9, that'll be plus 54. I've got my minus 3w here, minus 3w plus 9 plus 12, and that's equal to 0. Okay. Oops, I forgot to times my 27 minus 27 by 2. So this here, this will be minus 54. Minus 54. Okay, that's minus 54 there, so apologies for that. So now let's clean this up again. So, looking across here now, I notice some terms that will just cancel with each other. So I've got a minus 6w squared here and a positive 6w squared. So that will cancel with that. Have I got anything else? I should do. I've got 18w here, 18w there, and I've got a minus 36w there. So they will cancel with that. Okay, so they cancel. Is there anything else that cancels here? They should do. So I get 2w cubed. Okay, I get 2w cubed. I've got minus 12w squared, so that's good. Minus 12w squared, there's no other w squares. I've got, so that's done. Let's just put a tick, that's done. I've got minus 54 and plus 54, so that cancels. So that's fine. So minus 54. I think I've accidentally not timed something here. Yeah, okay. So that's 18w. So let me just, I've made a big mistake here. This here now, this is 36w. This is 18w. So this isn't cancelled. 18w. Okay, so I made a big mistake. So that, I forgot to times by 2, so it's now 36w. So that does cancel with that. But I've got an 18w left over. Minus 3w, so I get plus 15w. I know I've made a mistake somewhere, so it's very easy to make a mistake with these guys, so just be very careful. Plus 15w, and then at the end I've got 9 plus 12, giving me plus 21. And this is equal to 0. And this now is the cubic equation with these roots. So if I write what my p, q, and r and s are, so p, that would just be equal to 2. Q is going to be equal to minus 12. R will be equal to 15. And my S is equal to 21. And there we have it, that's question 2, fully complete. Moving on to question 3 now, we have a question here dealing with proof by induction. So we've got a proof by mathematical induction that for n belonging to the naturals, that this summation here is equal to n over 2n plus 1. Okay, so 6 marks for this. So the best thing to do for any proof by induction question is to try and think about what you need at the end. So to figure out what I need for the end of this question, well, we're going to say let n be equal to k plus 1, right? That's always the last step of a proof by induction. So if n is equal to k plus 1, and if I sub that in here now, where my n's are, what will I get? Well, I'll get k plus 1 over 2 lots of k plus 1, so that's 2k plus 2, and then add an extra one, so I get 2k plus 3. Okay, so this is what I need at the end. Okay, so that helps gives us a bit of an idea of what we should be ending up with. So now let's start the proof by induction. So the first case for any proof by induction is let n be equal to 1. I mean, you can let it be equal to a different value, but n equals 1 is always a very common one. So let n equals to 1. So what do I get on the left hand side? Well, left hand side, well, that's going to be equal to 1 over 2 lots of 1 minus 1. So it's going to be 1 over, so that bit will be 1. two lots of 1, so that's 2, plus an extra 1, that'll be 3, so it's 1 times 3, so that's equal to 1 over a third. Okay, so 1 over 3, a third, and then the right hand side, if we just do that over here, what will I get for the right hand side? Let n equal 1, so it's going to be 1 over 2 times 1, which is 2, plus an extra 1, so I'm going to get 1 over 3. Okay, so the right hand side is equal to the left hand side, so therefore true for n equals 1. Therefore, true for n equals 1. Okay, so that's the base case proved. Let's carry on now. So what we say next is that we're going to assume it's true for n equals k. So, assume true for n equals k. Okay, so if we assume this is true for n equals k, what would we end up with? Well, what we'd have is the summation going from r equals 1 to k, and it'd be this summation here, so it'd be 1 over 2r minus 1 times 2r plus 1. And this would be equal now, so if you put k in here, it'd be k over 2k plus 1. Okay, so just replace my n's with k. So it'd be k over 2k plus 1. Okay, so we're saying that's true, so this is true. Okay, so we've assumed it's true for n equals k. The next step now is to let n be equal to k plus 1. So let n be equal to k plus 1. Okay, and once we've subbed this n equals k plus 1 in, at some point once we've simplified, we should end up with this expression here, this k plus 1 over 2k plus 3. So I let n equal k plus 1, how can we work out this series, the summation? Well, let's rewrite the summation. So it's going from r is 1 up to k plus 1. Okay, well, remember for a series, so it's 2r minus 1, 2r plus 1. If I want the k plus 1 term, that would be the kth term plus the next one coming up. So the next term in the sequence after the k. So that'll be this term plus the next one. So if I write this down again, and we already know this is true, right? We've assumed it's true. So 2k plus 1. Well, my next term now will be this expression here, but with k plus 1 being subbed in for my r's. So let's write that down. So that'll be plus 1 over 2 lots of k plus 1, so that's 2k plus 2 minus 1, so I get 2k plus 1. Same here, but instead of it being 2k plus 1, it'll be 2k plus 3, because that's 2k plus 2 plus an extra 1. I get 2k plus 3. Okay, now what we need to try and do is get it over a common denominator, and this is nice and easy because that's a 2k plus 1, this has a 2k plus 1, so all I've got to do is times this bit here by 2k plus 3. So that gives me k lots of 2k plus 3 plus 1 all over 2k plus 1 times 2k plus 3. Now what we can do is we can expand this, and notice now we've got a 2k plus 3, that's what we need in the denominator. We've got a 2k plus 1 times 2k plus 3. So what we might expect here at some point is that the numerator will factorise, and then we can cancel terms. Okay, so let's keep expanding this numerator and simplifying. So k times 2k plus 3, so that'd be 2k squared plus 3k plus 1. And this is all over 2k plus 1 times 2k plus 3. Now we can try and factorise this numerator, which factorises quite nicely. So I do it all the way up here. So this 2k squared plus 3k plus 1, this will factorise, and this will give you 2k plus 1 times k plus 1. This is over, still the same denominator, so 2k plus 1 all over 2k plus 3. And this is perfect, right? Because now I can cancel my 2k plus 1 with that 2k plus 1, and all I get left with is k plus 1 over 2k plus 3. So therefore, this is equal to k plus 1 all over 2k plus 3. Perfect. That's exactly what we needed. So now what we can say is that this general result, so general result is true for n equals k plus 1. K plus 1. And we've just got to finish with a little comment. So if I write the final comment up here, so as this is true for n equals 1, and we assumed it was true for n equals k, and true for n equals k, this implies, so this implies true, that is true for n equals k plus 1. So therefore it's true for all n that belong to the naturals. So I'm not really good at doing this symbol, but there we go. So it's true for all n that belong to the naturals. So there we go. That's question 3 fully complete. Moving on to question 4 now, we have a question here on 3D vectors. So it's a pretty brief question, and what it's asking is, can we determine whether this line here, so we've got the line L with this equation, whether it intersects this plane pi at a single point, does it lie in pi, so lie on the plane, or is it parallel to pi without intersecting it? So 5 marks for this. So let's jump straight into it. Now there's a couple of ways you can actually do this. The easiest way, I think, is to consider the direction vectors. So first let's write the vector equation for L. So if I call it R, so R equals, well, my position vector will be the opposite here. So because it's x plus 2, my first one will be minus 2. This is minus 5, so that'll be 5. And this is minus 4, so that'll be 4. Okay. And then we need the direction vector, so lambda lots. Well, my direction vector is just simply the denominator of these fractions here. So it's 1, minus 1, and minus 3. And we don't change these, so it's just 1, minus 1, and 3. Sorry, minus 3. Okay. So now we've got these. That's my direction vector here. I've got this plane here, and this is my direction vector here. So that's my direction vector. So now, if I consider using the dot product for these two direction vectors, let's see what result we actually get for this, because this might help us prove something. So if I find the dot product, so I've got 1, minus 3, dotted with 1, minus 2, 1. So 1, minus 2, 1. Let's see what we get. So this is going to be equal to 1 times 1, 1 times 1, plus minus 1 times minus 2, plus minus 3 times 1, plus minus 3 times 1. Okay, 1 times 1 is 1. Minus 1 times minus 2 is 2, so that's 1 plus 2, plus minus 3 times 1, so that's minus 3. Okay, 1 plus 2 is 3, minus 3 off. We're going to get 0. Okay, so this is equal to 0. Now, if you calculate this dot product here for the two direction vectors, and your result is equal to 0, and don't forget this is a plane, what it means is that the line must be parallel to the plane. So the first thing we can say, therefore, is that the line is parallel to capital Pi. So my capital Pi is not very good, but there we go. So it's parallel to the plane. But now we need to consider whether it actually lies on the plane as well. So what we've got to consider here is a point on the line L, and then consider that point. We can then substitute this into the plane and see if it still lies on the plane. So the easiest point to consider for the line L, so if I call the point P, so looking at our equation here, minus 2, so we've got x plus 2, y minus 5, z minus 4. The easiest point is just to consider the origin, so 0, 0, 0. Well, for that, x must be minus 2, y must be 5, and z must be 4. Okay, so the point P I'm going to take will be minus 2, it'll be 5, and then 4. Okay, so again, use this point now. If we use our direction vector here, substituting this point in, What we should get, if it does lie on the plane, is -7. If it doesn't, then it doesn't lie on the plane. So, subbing this in now, I'm going to get 1 times -2, -2 times 5, and then 4 times 1. So if we do that, so subbing into the plane now. So that's going to be 1 times -2 plus 5 times -2 plus 5 times -2, and then finally 4 times 1. So let's just double check I've not made any mistakes. Yeah, that looks good. So that's going to give me 1 times -2, that's -2. 5 times -2 is -10, and then we've got plus 4. Well, -2 minus 10 is -12, plus 4, that's going to give me -8. So this clearly isn't equal to -7, right? So -8 is not equal to -7. Okay, so this would have been a contradiction if we'd have said -8 is equal to -7. So therefore P does not lie on the plane. So now the final comment we can make, so if it doesn't lie on the plane but it's parallel, so what we can say therefore is that L is parallel. So it's parallel to pi, but it doesn't lie in the plane, but not in the plane. And there we have it. So it's quite a brief question. There's a much trickier 3D vectors question much later on in the paper. But there we go. That's question 4 fully complete. Moving on to question 5 now, we have a question here dealing with complex numbers. So a few different parts of this question. So let's jump straight into part A. So part A gives us a bit of information. We're given a few complex numbers here, Z1, Z2 and Z3. And these are plotted in this Argand diagram above. And part A just asks us to explain why Z1, Z2 and Z3 can all be the roots of a quartic polynomial equation with real coefficients. Okay, so 2 marks for this. So for part A, well, the key thing to understand for complex numbers, and especially complex roots in this case here, because that's what we're dealing with, the key point is that complex roots of a polynomial, so complex roots of a polynomial, you've got to remember these occur in conjugate pairs, right? So complex roots of a polynomial occur in pairs, or they are in pairs, right? So the issue is here now, if you've got Z1, Z2 and Z3, well, we've got the complex conjugate here of Z2, and then we'll have Z3. So the issue is here now, we've got Z2, the conjugate of Z2, conjugate of Z3, and we've got Z1, Z2 and Z3. So the issue is we've got 5 roots there, but remember a quartic polynomial, so a quartic polynomial only has at most 4 roots. So the issue is we've got too many roots, so therefore these can't be all the roots of a quartic polynomial. We'd have too many roots. Okay, so too many roots. Okay, so that's just the idea there. We've got too many roots for part A. For part B, we've got a little bit here. So what I'm going to do, I'm just going to clear part A just to make sure I've got enough room for part B. So we've got to show that the argument of Z2 minus Z1 over Z3 minus Z1 is equal to pi over 4. Okay, so let's put these out individually. So Z2 minus Z1. Okay, so our Z2 is up here, that's minus 1 plus 2i. So minus 1 plus 2i minus Z1, which is minus 2, so that's plus 2. This is all over. So if I do underneath now, Z3 minus Z1. And what I'll do is I'll just simplify these in a second. So that will be equal to Z3 minus Z1. So that's going to be, where's Z3? 1 plus I. So 1 plus I. And again, we're taking off Z1, so that's minus minus 2, which is the same as plus 2. Okay, so now my numerator will simplify to 1 plus 2, so that's minus 1 plus 2, so that's 1 plus 2i. Just be careful you don't miss your own negative sign like I just nearly did. And on the denominator, I've got 1 plus 2, so that's 3 plus I. So that's 3 plus I. Okay, so now we just got to find the argument of this. Okay, so find the argument of this. Well, what I need to do first though is deal with this denominator. Okay, so to deal with this denominator, we need to multiply by the conjugate. So that would be 3 minus I. So remember, it's the opposite sign here. So times 3 by 3 minus I. Do the same with the denominator. 3 minus I. Okay, so if we do that over here, and again I'll have 3 plus I in the denominator, multiplied by 3 minus I. 1 times 3, that's 3. I'll have minus I here, plus 6I, so 6I minus I, that'll give me positive 5I, and then minus 2I squared, minus 2I squared. Remember, we'll deal with the I squared in a second. Let's just deal with the denominator first. 3 times 3 is 9. Now remember, this is the difference of two squares, so you can jump straight away to doing 3 times 3, so that's 9, and then I times minus I to give you minus I squared. The other two terms will cancel, so I get 9 minus I squared. And remember, I squared is equal to minus 1. Okay, so minus 2 lots of minus 1, that's going to be plus 2. So my numerator now, in this case, that's going to be 3 plus 2 plus 5i. So I'm going to get 5 plus 5i on the numerator. My denominator will be 9 minus minus 1, so that's 9 plus 1, giving me 10. Okay, so simplifying this now, I'm going to get a half plus a half I. Okay, so now we've just got to find the argument of this. Okay, so we've got it into its best form to work with now. Now we've just got to find the argument. So to do that, well, that would be we have to do the inverse of tan. So arctan or tan inverse. Because they're both a half, it'll be half divided by half, like that. Well, a half divided by a half, that would be the same as arctan of 1. And remember, arctan of 1, and because we're in radians here clearly, because this is pi over 4, well, this is just going to be arctan of 1, which if you do it on your calculator, or if you just know it by memory, that'll be pi over 4. So there we go. So we've shown that the argument here of z2 minus z1 over z3 minus z1 is pi over 4. So that's part B. Part C is just a little bit of a follow-up from that. It says, hence show that arctan of 2 minus arctan of a third is equal to pi over 4. So, remember, when you're dealing with arguments, you can split them up here. So, treating this separately now, this would be the same as the argument of z2 minus z1 minus the argument of z3 minus z1. Okay, but remember, we said z2 minus z1, that's 1 plus 2i. So this is the same as the argument of 1 plus 2i minus the argument z3 minus z1. We said that was 3 plus I. 3 plus I. Well, taking the inverse tan now of both of these, so that'd be arctan. That'll clearly be 2 over 1, so that'll just be 2, so arctan of 2, minus the argument, so this would be, to get the actual argument, you take the inverse of tan, so arctan again of 1 over 3 in this case, so 1 over 3, and notice this gives us exactly what we've got here, and this is just what we've done already, so this is pi over 4. Okay, so that's just a little follow-up from part B there, just showing it in that case. And then finally for part D, we've got a copy of figure 1 here, labelled on diagram 1. Now, the diagram 1 is just the exact same as this argon diagram here, so I will just do it on figure 1. We've got to shade the set of points of the complex plane that satisfy this inequality here. So the modulus of z plus 2 being less than or equal to the modulus of z minus 1 minus I for 2 marks. So where do we begin with like a question like this? Well, what I'm going to think about first is these 2 points, right? So I've got z plus 2 less than or equal to z minus 1 minus I. Well, let's get this in the form that we work with. So this now, this will be z minus, to get plus 2 that must be minus 2. Okay, so that's the left hand side of the inequality. It's going to be less than or equal to, I've got z, so if we write that down, I've got z, I'm going to do minus again, we always do minus, and to get minus 1 that must be 1 here, minus, so that'd be minus of a positive, so that gives me the minus 1, and then same here I must have positive I. So now, these are my 2 points that I'm dealing with. I've got -2, and notice -2 is my z1 here, so we've got this point here, and I've also got 1 plus I, which notice is z3. So we're going to have these 2 points involved in this question. So now, what I've got to consider here is that if I join these points up, so that was a really bad line, let me just undo that. So I'll try again if I can join them up. So z1 to z3. What I need here is the perpendicular bisector of this z1 to z3. Okay, so the first thing I can do is work out the midpoint, and then I can also work out the gradient. Okay, and we can combine them to work out the equation of the perpendicular bisector, and then we just need to shade from the perpendicular bisector. So if we work out the midpoint, so if I just call it MP, so for the midpoint, well, that'll just be the average of z1 and z3. So if I add z1 and z3 together, that's going to be -2 plus 1 plus I. Okay, well, doing that, that's just going to give me -1 plus I. And then we have to divide this by 2. Remember, it's the average of it. So if I divide it by 2 here, do the same here, that's going to give me -1/2 plus I over 2. Okay, so that's the average there. So that's my midpoint, so that's roughly going to be, I don't know, about there, let's just say. Okay, and now we can work out the gradient. So the gradient, well, that's going to be the gradient formula, so that's going to be y2 minus y1 over x2 minus x1. So I'm going to do z3, so that'll be my 1 coordinate there, because it's 1 unit up, plus I. That's going to be 1 minus 0, because that has just no height, it's just -2 along on the x-axis, so that's a 0. So 1 minus 0 over, and it's going to be 1 minus -2. So that's going to give me 1 over 3, but remember we need the perpendicular gradient here, so we take the negative reciprocal. Okay, so my perpendicular gradient is going to be equal to -3. So now we've got a gradient, we've got the midpoint here. Now I can just use the formula for the equation of a straight line to obtain the equation of the perpendicular bisector. So if I just do that up here, so remember the formula is just y minus y1 is equal to m lots of x minus x1. Well, plugging all this in now, so y minus y1, so my y1 is a half basically, I over 2, we'll just call it a half. So it's going to be y minus a half. That's going to be equal to -3, our gradient is -3, x minus x1, which would be minus a half, so that'd be plus a half. Okay, so that's that. Now we just simplify all this, so I've got y minus a half still, minus 3x, minus 3 over 2. I'm being attacked by my cat currently. So if I carry on this now before I get attacked fully, minus a half. So I take that across to the other side, so that's going to be y equals minus 3x, and then I've got minus 3 over 2 plus a half, so that'd be minus 2 over 2, or minus 1. So y equals minus 3x minus 1. So it's currently jumping on my back. So y equals minus 3x minus 1. So that's my equation now. So if we just plot that, well, it's going to cut through here at -1. So it's going to cut through somewhere there. And if we join this up now, what you'll actually notice is that it goes through Z2. So my cat's jumping over everything. Right, okay. So it's going to cut through here. Let me just undo that, that's not very good. It's going to cut through roughly like that. Okay, it does actually cut through Z2. So now we've just got to deduct where it cuts through, or where it's closer, because it's saying where is it Z plus 2 less than or equal to the distance of Z minus 1 minus I. Well, remember this Z plus 2 is this point here, your Z1, and this Z minus 1 minus I, that's this point here. So which side gets me closer to Z1? Well, that's clearly going to be anything here. If I pick this point here, I'm closer to Z1 on this side here than I am on this side. So we're going to have to shade everything across here. Okay, so what I'm going to just quickly do is I'm just going to rub out this little line here, just so you can see it, and then I'm going to shade it all. So if I shade it all now, what you need is everything to the left of this line. And there you have it. So that's part D. So that's just everything that you need to shade. Okay, so that's your line, and that's your shaded area. And there we go, that's question 5 fully complete. Moving on to question 6 now. Here we have a question that's dealing with series and summation, but it's a bit of a sneaky question. It involves a little bit of stats, but there's not really too much stats behind it. You just got to use a couple of formulas. Mainly in part B here, we're using the standard summation formula to find the standard deviation. So nothing too crazy. You've just got to not be put off by the actual format of this question. So let's jump straight into it. So part A. So what have we actually got here? So we've got this art display that consists of an arrangement of n marbles, and it's telling us that when they're arranged in ascending order of mass, the mass of the first marble is 10 grams, and then the mass of each subsequent marble is 3 grams more than the mass of the previous one. So our nth term basically is 7 plus 3r grams. Okay, so what we want is that the mean mass in grams of the marble, and we can actually show that it's equal to a half 3n plus 17. Okay, so remember your formula for the mean. Well, that's going to be 1 over n, and in this case it'll be the summation of my nth term, which is 7 plus 3r. Okay, so it'll be the summation of 7 plus 3r, where r is 1 all the way up to n. That's a 1 all the way up to n. Okay, so dealing with this summation now, I'm going to have 1 over n on the outside. In here now, well, we're taking a summation here of 7 plus 3r, so we can use linearity. We can split this up into 2 summations. So this is going to be the summation of 7 from 1 to n, but remember, if you're taking the summation of a number, then you can times that at the front. So it's going to be 7 lots of 1 from r is 1 to n. Same again here, plus 3 lots of the summation from r is 1 to n of r. Okay, and you need to use your standard formulas now for r, and in part B you will need r squared. So if we close that and we'll actually work this out, that's going to be 1 over n still on the outside. In the bracket now, if you take this summation here from r is 1 to n of 1, that'll be n times it by 7, you get 7n, okay, plus 3 lots of r. Well, remember the standard result for r, the summation for r is right over here, that's going to be n over 2 times n plus 1, n plus 1, okay, so you've got 3 lots of that, so it's going to be plus 3n over 2 times n plus 1. Okay, now we just need to keep simplifying here. Well, if I've got 1 over n on the outside and I've got 2 lots of n here, I've got 7n, I've got 3n over 2, we can start dividing. So 7n times by 1 over n, that's just going to give me 7. 3n over 2 times 1 over n, then that'll just cancel. So what I'm going to get here is plus 3 over 2 lots of n plus 1. Okay, so that's okay so far. Now what we need to do is just carry on simplifying. So if I get this over a common denominator, what I'm going to get is times it by 2, so that'll be 14 plus 3 lots of n plus 1 all over 2. And now expand this, so that's equal to 14 plus 3n plus 3 all over 2. Simplify that now, so that'd be 17 plus 3n over 2. And then finally, we can just apply this factor of a half here to the front like this. This will be a half lots of 3n plus 17. So there we have it. So we've shown the mean marbles here, x bar, is equal to a half times 3n plus 17. Okay, so that's part A done. Let's have a go at part B now. So it's a bit longer and a little bit more complicated. So we're told that there's 85 marbles in the display, and we've got to use the standard summation formula to find the standard deviation here. So remember the formula for your standard deviation, if I write up here, well, that's going to be equal to the square root of sigma x squared all over n minus sigma x over n all squared. So this is your mean squared. Okay, so let's have a go at working out sigma x squared first. Well, sigma x squared, that's the same as the summation of your nth term all squared, so 7 plus 3r all squared. this now, treat it as double bracket and expand this. So I've already done the expanding, but it should hopefully be pretty straightforward. It's just double brackets, obviously. And remember, we're going from r is 1 up to n. Again, r is 1 up to n. So what will this be? So this will be 49 plus 42r plus 9r squared. Like so. So now we're going to do this just like we did with the other one. We're splitting this up into 3 different summations in this case. And we notice you've got the formula for r, and we're going to use the formula for r squared as well in part B. So splitting this up now, this would be 49 lots of the summation of 1. So this would be just 49n. Just like we did in part A, but this time it's 49 rather than 7. I've got 42r. So if we write this out in full, this will be 42 lots plus 42 lots. I was right, 42, and then it's going to be n over 2 times n plus 1, just like we used in part A. And then finally, for this part here, well, it's 9 lots of r squared. And remember, r squared is n over 6. So this is r squared. N over 6, n plus 1 times 2n plus 1. Okay, so it's 9 lots of n over 6 times n plus 1 times 2n plus 1. Okay, so now here at this point, you've just got to keep simplifying, okay? So this will be 49n still at the front. So I'm probably doing this in a few steps. If you can work ahead faster, then that's absolutely fine. But I'm going to take it quite slow. So 42 divided by 2, that gives me 21n plus 21n. Lots of n plus 1. And then I'm going to have 9n over 6. And these 2 brackets again. So n plus 1. 2n plus 1. So now let's keep simplifying. So this is going to give me 49n plus 21n squared plus 21n. This n plus 1 times 2n plus 1, so that'll give me 2n squared plus 3n plus 1. So, multiplying each term now by 9n over 6, so that'll give me 18n cubed over 6, so that's plus 3n cubed. Plus 3n cubed. 9n over 6 times 3n, well, I can't do anything with that, that's just going to give me 27n squared over 6. Plus 27n squared over 6, and then finally 9n over 6 times 1, I just get 9n over 6. Okay, so now we can get this simplified. So if you simplify all this, I've just kind of jumped ahead and done it, but just adding your like terms here, this will be 3n cubed. You'll get 51n squared over 2, and then finally 143n over 2. Okay, so now we can use the formula for the standard deviation, this formula here. Remember, this is your sigma x squared, so this is sigma x squared. So we're going to have to divide this by n in the formula. So if I use the formula now, I'll do it over here, so final answer. Okay, so the square root, sigma x squared over n, so that's going to be 3n squared plus 51n over 2. And then finally 143 over 2. Minus, so this is now your mean. Well, your mean can just be calculated by plugging 85 into here. So this would be a half, 3 times 85 plus 7e. And what you get for the mean is that this is equal to 136. Okay, so just do it up here just to show it. The mean is equal to 136. In other words, this is your sigma x over n. Okay, this is the same thing here. So now, plugging this into my formula, minus 136 squared. Well, put n is equal to 85 into this formula now. Okay, so plug all that in, and I'll put this in on my calculator, and what you should get to one decimal place is 73.6 grams for the standard deviation. And there we have it, so that's your standard deviation. So there's quite a lot of, little things to watch out for on that question, a few little tricky parts, but overall it's just a standard summation formula question. We split the series up into separate parts. Okay, so there we go, that's question 6 fully complete. Moving on to question 7 now, we have a question here that's looking at the roots of a complex cubic polynomial here, and part of the question is looking at using the roots of a polynomial to answer this. Okay, so let's jump straight into this. So part A, it asks us to solve completely the equation f of z equals 0. So f of z is this cubic polynomial here, so z cubed minus 8z squared plus pz minus 24. And we know p is just a real constant. So it's got distinct roots, it's got alpha, beta, and alpha plus 12 over alpha minus beta. Okay, so we need to get these roots. So how do we get these roots? Well, the first thing we can know is that we're going to need to work out a value for alpha beta. So alpha beta, how can we get this value? Well, the first thing I can know is that, imagine this is alpha beta, and I'm going to call this one gamma. So that's the root gamma. So I know alpha plus beta plus gamma, well, that's going to be equal to minus b over a. So minus b over a. Well, minus b over a, well, my b here is minus 8, so minus 8 is 8. So what it's going to be is 8 over 1. So alpha plus beta plus gamma, but my gamma is this here. So let's substitute that in. So do that over here now. Plus alpha plus 12 over alpha minus beta, and we know it's equal to minus b over a, where minus b over a is equal to 8. Okay, so that's equal to 8 like so. Well, we can simplify here, right? Alpha plus alpha, that's equal to 2 alpha. I've got beta minus beta, so they cancel, and I've got 12 over alpha plus 12 over alpha, and this is equal to 8. So now, what can we do here? Well, I can multiply through by alpha. So if I do that, that will give me 2 alpha squared. If I multiply this by alpha, I'm just going to get plus 12. And then if I multiply the other side by alpha, I'm going to get 8 alpha. Okay, so getting this as a quadratic now, which is equal to 0, this is going to be 2 alpha squared plus, minus 8 alpha plus 12, and that's equal to 0. So now we can simplify here, dividing each term by 2. So that's going to be alpha squared minus 4 alpha plus 6 is equal to 0. And here now, we could have a look if this factorises, but a quick inspection, you'll find out that this doesn't actually factorise. So we're going to have to use quadratic formula. So quadratic formula, well, I'm just going to write it as, in fact, I'll write it as alpha. So alpha is equal to, so it's going to be minus b, but minus b here would be minus 4, so that's going to be 4, plus or minus the square root of b squared, so 16, minus, do it all in a bracket, 4 times 1 times c, where your c is 6. So 4 times 1 times 6, and we can close the bracket. And this is all over 2a, where a is equal to 1, it's the coefficient of it, alpha squared here. So that's going to be 2 times 1, which is 2. So let's just keep simplifying here now. So it's going to be 4 plus or minus 16 minus 24. So 16 minus 24, that gives me the square root of minus 8. And this is all divided by 2. Okay, keep simplifying. So it's going to be 4 plus or minus, this is alpha still, 4 plus or minus. So simplifying this square root of minus 8, so the square root of minus 8. So if you're unsure how to do this, it should hopefully be pretty easy, but you can split this up into 2 square roots, square root of minus 1 and 8. Well, the square root of minus 1 is I. The square root of 8, well, that would be root 4 root 2, so root 4 root 2, which is equal to 2 root 2. Okay, so this would be 2i root 2, so 2i root 2. And now this is divided by 2, and then we can divide each term by 2. So this is going to be equal to 2 plus or minus, sorry, where have I got 2? So 2 plus or minus I root 2. So that really wasn't that complicated. Not sure why I tripped up there. So 2 plus or minus I root 2. Okay, so what I can say now is that them are two of my roots, so therefore if we call it alpha, that's equal to 2 plus I root 2. Then if I say beta is 2 minus I root 2. Okay, so that's alpha beta, but we need this gamma here. Okay, we need that third root. But we can use this, right? This only uses alpha and beta. So let's use this. So we know alpha plus 12 over alpha minus beta should be equal to 0, right? That's my root. So if I set that up now, that's 2 plus I root 2. So I'll just split this off here. Underneath, so 2 plus I root 2 plus 12 over this. Minus beta, which is minus, and then we do it in a bracket, 2 minus I root 2. Okay, like so. So now, the first thing I'm going to have to do here is multiply this middle term here by the conjugate, 2 minus I root 2. So, if I just write it out again, 2 plus I root 2 plus 12 lots of the conjugate do the same with the denominator. Like so. And then we subtract this beta term here, so minus 2 minus I root 2. So now, we're going to have to simplify this, so I've kind of run out of room here. So what I'm going to do is I'm just going to change my pen to yellow and then do it at the top. So, I'm taking this all the way to the top now, all the way up here. So if we do this at the top, well, let's just simplify the middle term. So this would be 24 minus 12 I root 2. So 2 plus I root 2 plus 24 minus 12 I root 2. This is all over now. So this is the difference of two squares, remember, so the easy way to work this out is square the first two terms of each bracket and then multiply the first two terms together and then multiply the last two terms together. So 2 times 2, so that's going to be 4. And then if you multiply I root 2 with minus I root 2, that'll give you minus I squared times 2, which will just give you a positive 2. Okay, so it becomes 4 plus 2. And then this final bit will be minus this 2 minus I root 2. So minus 2 minus I root 2. So I'm kind of running out of room here. It's a bit of a tight fit. So now we can keep simplifying. This is going to be 2 plus I root 2. So this is 24 over 6, so that'll be 4 plus 4 minus 12 I root 2 over 6, that'll be minus 2I root 2. And I've got minus 2 plus I root 2. Okay, just multiply that out by the negative. Plus I root 2. Well, if you look at each term here, what will actually happen? Well, you've got 2 lots of I root 2 and you've got your minus 2 I root 2. So they cancel with that. And I've got 2 plus 4 minus 2. So that just gives me 4. So my third root here, my final root gamma is equal to 4. Okay, so 3 roots are my alpha and beta, which were basically the plus or minus, so it's 2 plus or minus I root 2. And we've also got 4. Okay, so them are the 3 roots there for part A. So if we just clear this now, just to carry on with part B. Well, for part B, we worked out that one of the roots is 4, so root of 4. Well, if we know that a root is equal to 4, we've got a root of 4, well, using the factor theorem now, so what that is that the fact that f of 4 will be equal to 0. Substitute 4 into this cubic polynomial here, set it equal to 0, we can obtain a value for p, nice and easy. So, doing that now, that's going to be 4 cubed minus 8 lots of 4 squared plus p lots of z, where z is 4, so 4p minus 24, this is equal to 0. So now, just putting all this in on your calculator, it's going to be 64 minus 128 plus 4p minus 24. And this is equal to 0. Simplify this side, your left hand side of your equation, you get 4p minus 88 is equal to 0. So therefore 4p is equal to 88. Divide each side by 4 to get 88 over 4, or get p equals 22. And there we have it. So that's the value for p. You should get 22. And that gives us question 7 fully complete. Moving on to question 8 now, we have a question here on 3D vectors, and this is quite a tricky question. As you can see, there's a lot of context to this question, and it's split into 4 different parts. So let's have a look at what we're dealing with. So we've got a gas company that maintains a straight pipeline that passes underneath a mountain, and this pipeline is modelled as a straight line, and then one side of the mountain is modelled as a plane. Okay, so it says that there are access ways from a control centre to 2 access points on the pipeline. So if we model the control centre as the origin, O, and then the 2 access points on the pipeline have these coordinates P and Q, where the units are in metres. So part A just asks us to find a vector equation for the line PQ, giving our answer in the form R equals A plus lambda B. So hopefully, as tricky as this question is overall, hopefully part A isn't too bad. Pretty standard, so part A. So we're working out PQ. So for PQ now, remember we kind of work backwards, so for PQ this is going to be Q minus P, okay? Using these coordinates, so Q here and then P here. So if we do that, what will we get? So that'll be 300 and minus 50 minus my P here, my coordinates for P, so that's minus 300, 400 and minus 150. Okay, let's do that. So 300 minus 300, that'll give me 600. 300 minus 400 gives me minus 100. And then minus 50 minus 150, that'll give me positive 100. Okay, so let's close that. We've got this now. Now we just need to put it into this form here. R equals A plus lambda B. Remember, this is my direction vector here. So R is equal A. So A can be either P or Q. It's completely up to you, but I'm just going to use P here. So it's going to be minus 300, 400, minus 150, plus lambda lots of this. Okay, so plus lambda lots of 600, minus 100, and 100. So that's part A done for the first 2 marks. So as you can see for this question, apart from me scrolling down, there's not much room, but seeing as we need to keep reading the question, what I'm going to keep doing at each stage is just clearing it. So that's part A done. So part B tells us that the equation of the plane is 2x plus 3y minus 5z is equal to 300. And what it's saying is that they want to create a new access way from this side of the mountain to the pipeline. So the access way consists of a tunnel of the shortest possible length between the pipeline and the point M, and that's the coordinates for M are 100, K and 100 on this side of the mountain, where K is just a constant. So this is where this question gets a bit tricky. The first thing we have to do is work out a value for K. Okay, so how do we work out that value for K? Well, we know the equation of the plane is 2x plus 3y minus 5z is equal to 300. So we've got this point here, M 100, K 100, but if we sub this into this equation of the plane, we can work out a value for K, right? So that's going to be 2 lots of 100, 2 lots of 100, plus 3 lots of K, we don't know what K is yet, and then minus 5 lots of 100, so minus 500. This is equal to 300. So if we simplify this now, this will be 200 here minus 500, so that's going to give me 200 plus 3k minus 500. So what I'm going to get, if I simplify all this in total, is I'll get 3k is equal to 600, taking it across to the other side, and then 3k is equal to 600, so I can divide both sides by 3 to get k is equal to 200. So what we know now is that the coordinates of M is 100, 200 and 100. Okay, so we can use this now to work out the coordinates of the point at which the tunnel meets the pipeline. So the first thing to know is that M is a point on the mountain. So M, point on the mountain. And we know that X is just a general point on the line, or the pipeline in this case. So X is a general point on the line. So using that information now, we can work out a vector equation for mx. So mx. Well, how do we do that again? Working backwards. So that's going to be x, which is just my general point. So that was what we had from part A. So that's going to be minus 300, 400, and minus 150. So I'm just making sure I don't accidentally write anything down incorrectly, because there's a lot of different vectors here. So plus lambda lots of 600, 600, minus 100, and 100. And we need to subtract m off this. And remember, m is this point here. So we're going to minus, so I just do it to the side here. So we're minusing off 100, 200, and 100. So this is getting a little bit messy, but hopefully you can see where we're going. So I'm going to work this out now. But remember, this is minus 300, minus 100, 400 minus 200, and then minus 150 minus 100. So simplifying all that, what you'll get is that mx is equal to minus 400 plus 600 lots of lambda, and then keep doing this for each one. So I've just skipped ahead to do all these. 600 lambda, that'll be 200 minus 100 lambda, and then finally minus 250 plus 100 lambda. Okay, but it's important to know that the mountain line here that we have is perpendicular to the direction, right? You think about how this pipe's going down. So let me just do that straight. So the pipe that's coming down here, what it's saying is that the pipe that meets it here is perpendicular, right? So you should know for vectors that if you do the dot product of two perpendicular vectors, it'll be equal to 0. So doing that now, what I can say is minus 400 plus 600 lambda, and then this basically it's just this here, so 200 minus 100 lambda minus 250 plus 100 lambda dotted with, so now we dot it with the direction, okay, so 600 minus 100 and 100. So now you've got to work all this out. So what I'm going to do is I'm going to do this on this side over here. In fact, let's just work all this out. We should have enough room on here. So this is a very long question. It might be about a 20-minute video, this overall. So doing this over here now, what do we get? Well, we're going to get minus 240,000 plus 360,000 lambda. So like I said, this is quite a long, tedious question. Plus minus 20,000 minus 20,000 plus 10,000 lambda, and then same again here, plus minus 25,000, and then finally plus 10,000 lambda. So simplifying all this now, and we know this should be equal to 0, so this is equal to 0. So I've skipped ahead and done this already, but what you should get is 285,000, sorry, minus 285,000 plus 380,000 lambda is equal to 0. So take this 285,000 across and then divide by 380,000, and what you'll get is that lambda is equal to 3 over 4, or 0.75. So we've got our lambda value now. All we need to know is use that lambda value for my R equation. Okay, so using that with my R equation, so what that'll be is R equals, so it was my R equals from part A. So we had for part A minus 300 400 and minus 150 plus lambda, but that's 3 over 4 for the direction, so it's 600 minus 100 and 100. And then if you work out each one of these individually, which I've already done, you get your coordinates. So your coordinates will simply be 150, 325 and minus 75. And there we have it. So that's the coordinates of the point at which the tunnel will meet the pipeline. So coordinates. Okay, so that's part 1 done for B. Now we have to work out the length of this tunnel. Okay, so the length of this tunnel. So what I'm going to do first is I'm just going to clear all this work here so we can see what we've got. So to find the length of this tunnel, well, I'm just going to have to use the distance formula equation. So length of the tunnel well, what I'm going to do is I'm going to use 150. So I'm using my which equation have I got here? So that's my coordinates at which the point at which the tunnel meets the pipeline. So I'm going to do the distance from 150. So if we do that, it's going to be the square root of 150 minus the distance here. So it was my original distance of 100. So minus 100 and then square it. Again, do the same for your next coordinates, so it's 325 minus 200. And then finally plus minus 75 minus 100, all squared. Okay. Put all this on your calculator, and what you should get is 221 meters for this part here. So that's simply what you've got to do for the length of the tunnel. So it's your coordinates of where the point at which the tunnel meets the pipeline, and then you go in from the plane in essence, basically. Okay, so that's the length of the tunnel, 221 meters. Part C says to determine whether the company should build the new accessway. So it says it's only practical to construct the new accessway if it will be significantly shorter than both of the existing accessways. So that's OP and OQ. So we need to work out the length of each one. So the length of each one, well, again, just distance. So OP, so that's your coordinates here. So it's going to be the square root. So we do this one down here. Square root minus 300 squared plus 400 squared plus minus 150 squared, and then take the square root of the full thing. Do the same now for this vector here, OQ. So this is going to be the square root of 300 squared plus 300 squared and then plus 50 squared. Okay, put both of these on your calculator, and what you'll get for OP is approximately 522 meters. And then for this one here, OQ, again you'll get approximately 427 meters. Okay, so it says determine whether they should build the new accessway. Well, as the new tunnel is much shorter, the new accessway should be built. Because what it's saying is it's only practical to construct the new accessway if it's significantly shorter. Well, we got 221, so we had 221 meters. These two are clearly much larger. Okay, this is 427, this is 522. So therefore, the new accessway should be built. Should be built. Okay, and then finally, for part D, it just asks us to suggest one limitation of the model. Well, there's a couple of different things you could say. I think the clearest one to me would be the idea of the plane, right? It's saying that the side of this mountain is represented as the equation of a plane. But, I mean, if you've ever looked at the side of like a mountain, it's never completely flat, right? There's a lot of rocks, different like hill levels and stuff. So one limitation that I'd suggest is that the mountainside is unlikely to be completely flat. To be completely flat. So therefore, a plane might not be acceptable or appropriate. We'll say appropriate. Another comment you could make is the fact that the pipeline is modelled as a straight line. Clearly this pipeline isn't going to be it's going to have a thickness on this pipe, right? So a straight line might not necessarily be the best model for it. So that's another comment you could make. But for me, this is the clearest one that jumps out. So the idea that the mountainside is unlikely to be completely flat, and therefore a plane might not be appropriate for the model. So there we have it. That's question 8, fully complete. Moving on to question 9 now, we have a question here that's dealing with solid of a revolution. Okay, so we're given this function here, f of x, which is equal to 2x to the power of a third plus x to the power of minus 2 over 3, and x must be positive. And it tells us that the finite region bounded by the curve y equals f of x, the line x equals 1 over 8, the x-axis and the line x is equal to 8 is rotated through theta radians about the x-axis to form a solid of revolution. It tells us what the volume is, so it's 461 over 2 units cubed, and we have to use algebraic integration to find the angle theta. So this is quite late on into the paper, the penultimate question, and it's 8 marks, but as long as you're confident with integration, I don't think this question is too challenging. Okay, so let's write in the formula that we're going to need. So we know that the volume V, well, that's going to be equal, so it's always pi lots of the integral. We know the limit straight away. We're told that it's between 1 over 8 and 8. So 1 over 8 will be my lower limit. My upper limit being 8. And we're integrating the function here, f of x. So it'll be f of x squared with respect to x. And then to find the angle, theta, to which the region is rotated, well, I'm going to have to times this by theta over 2 pi. And remember, it's theta over 2 pi, not theta over 360, because we're working in radians for this question. And we know that they've told us here that this is equal to 461 over 2 units cubed. Okay, so we'll just say equal to 461 over 2. So, using that now, let's write this formula down again. So V will be equal to pi lots of the integral. So now, instead of f of x, I'm going to write out my actual f of x. So that's going to be 2x to the third plus x to the minus 2 over 3. This is all going to be squared with respect to x. And then again, times it by theta over 2 pi is equal to 461 over 2. So rather than doing it underneath, to square this, again, it's just double bracket. It should be hopefully nice and easy. So I'll write out what this will be. So if you square this, plus x to the minus 2 over 3. Well, this squared, this will give you 4x to the 2 over 3 plus 4x to the minus a third. And then finally, plus x to the minus 4 over 3. Minus 4 over 3. Okay, so again, we can rewrite this. So for the first part of this question, there's just a lot of getting this into the correct form to work with. But it's a good step in maths to always get things in a much easier form to work with. So 8, 1 over 8. So rewriting this now, this will be 4x to the 2 over 3 plus 4x to the third, minus a third even, plus 4x, so let me just undo that one, plus x to the minus 4 over 3. Okay, that's dx, and again, we'll times it by theta over 2 pi. This is equal to 461 over 2. Okay, so we've got something we can work with now. What I'm going to do here now is I'm going to perform the integration now. So, if I perform the integration here, what I'll do is I'll just write everything out fully, so everything's clear. But obviously, if you're confident at just simplifying everything straight away, you can just jump to that step. But for clarity, I'm going to write everything out in full. Oops, sorry. So let me just undo that integral sign. So I'm going to integrate now. Well, if you integrate here, add 1 to the power of 4x to 2 over 3. That would be adding 3 over 3 to it. So I'm going to get 4x to the 5 over 3. So with 4x to the 5 over 3, that's a 5. And then we divide it by 5 over 3, for example, right? Again, keep doing this with each term here. So your next one would be plus 4x to the 2 over 3. Just doing it off the top of my head, 2 over 3, and divide that by 2 over 3. And then your next one would be plus x to the minus a third, divided by minus a third. Okay. That's between 8 and 1/8. And then we'd have to times this by theta over 2 pi again. We know that'll be equal to 461 over 2. Okay, so again, let's just keep simplifying. Now at this point, we can actually just simplify. So I'll write it out in full again. So you could just save time by just skipping ahead. But I'm going to write everything out in full. So this would be 12 over 5. X to the 5 over 3. Plus 6x to the 2 over 3. And then finally, minus 3x to the minus a third. And then this is between 8 and 1/8. And we've got to times this by theta over 2 pi. Okay, so if I do that now, what I'm going to get here is inside here, when I sub in both of these limits and perform the calculations, what I'm going to get is that this is theta times 4,149 over 40. So I've already pre-done the calculations. And then we've got to times this by theta over 2 pi. And we know this is going to be equal to 461 over 2. So now, we just need to obtain theta. And well, to do that, I'm just going to have to simplify, right? So, simplifying here now, I can times this theta, this pi with this 4,149 over 40 here, and then multiply across. And clearly these pi's are going to cancel. So, what I'm going to get here is 4,149 theta divided by 2. So if you've got your 40 here, and then we times it by something over 2, then I'm going to get 80 as my denominator here. And this is going to be equal to 461 over 2. So now I've got to times this by 80, this right hand side. So if I do it all the way up here, so if I just change my pen colour so it's clear, yellow should be a nice colour for this. So I'm going to get 4,149 theta. That will be equal to 461 over 2 times 80. So that will be equal to 18,440. And now simply just to obtain theta, I've got to do 18,440 divided by 4,149. Do that on your calculator. And what you obtain is that theta is equal to 40 over 9 radians. And there we have it. So 40 over 9 is the angle theta for which the region is rotated. And that's question 9 fully complete. So finally moving on to the very last question now for this AS Core Pure paper, we've got to question 10, which is quite a long question, and it's dealing with matrices. So again, this is a very context heavy question. So it's looking at the population of chimpanzees in a particular country, which consists of juveniles and adults. So we're given this model here for a population. And the very first part just asks us to interpret the meaning of the constant A in the context of the model. So it's important to know what's going on. So my Jn plus 1 gives me my next population figure for the juveniles, and my An plus 1 gives me the next population figure for the adults. So this A here, so let me just get my pen. So what I'm going to do is I'm going to write down the sides for this question because it is quite like long. Obviously I haven't got much room here down at the bottom. I'm just going to write down the sides. So I'll do it in yellow. So pi. So what does this constant a mean in the context? Well, this a just represents the proportion. It represents the proportion of juvenile chimps. Proportion. So the proportion of juvenile chimps that survive and remain juvenile chimps. So quite a long opener, and remain juvenile chimps. Okay, so that's part A. So for part A represents the proportion of juvenile chimps that survive and remain juvenile chimps. Okay, so there's one marker there. Part B, so we're given a bit more information. We're told at the start of the study the total number of chimpanzees in the country was estimated to be 64,000, and then according to the model, after 1 year the number of juvenile chimps is 15,360 and the number of adult chimpanzees is 43,008. So we have to find, in terms of the inverse of this 2x2 matrix here. So to find the inverse of a 2x2 matrix, the first thing we should do really is just work out the determinant. So if we work out the determinant for this matrix, determinant, well, the determinant, remember, is this element here, so a times 0.82, so that's 0.82a, and then we minus 0.08 times 0.15, and if you do that on your calculator you'll get minus 0.012. Okay, so that's the determinant. So now, to work out the inverse, we do 1 over the determinant, so 1 over the determinant, let's call it det, and then we times this by the inverse matrix, or the matrix that we have to just do a little bit of work to. So the a and the 0.82, they change positions, so this is going to be 0.82 and that will be a there, and then my 0.15 and my 0.08, they become negatives, or if they were negatives they become positive, so think of them as the conjugates, so that would be minus 0.15, and then this one here will be minus 0.08. Okay, but we know the determinant. The determinant here is 0.82a minus 0.012. So if we plug that in now, I'm going to get 1 over 0.82a minus 0.012. Okay, and there we have it. If we just multiply this again by the matrix, 0.82 minus 0.15 minus 0.08, and then finally a. And that's it. So that is the inverse here of this matrix. So that's B part 1. B part 2, hence or otherwise find the value of A. So find the value of A. So it's a hence or otherwise question. So what that suggests is that this part of the question here, the previous part, will be helpful for solving this. Well, we're going to use this information that they give us now. So using the inverse now, what we can do is use the inverse. So if I write down the inverse, so A, 0.15, 0.82, so the inverse here of this matrix, and I times it by these population figures that they give us, so 15,360 and 43,008, we can work out a value for A, right? So multiply that through by 15,360 and then 43,008, we can work out a value for A. Now it's worth noting this part now will become quite tricky. There's a bit of manipulation that you've got to be careful with. So we know this now. This is what we just previously worked out, and this is why it's a hence or otherwise question. So if I write this out in full, this is going to be 1 over 0.82a minus 0.012, and then it's this matrix here, so 0.82 minus 0.08 minus 0.15 a, and then we times it by this. Okay, so I should just have enough room. And 43,008. Okay, and if I close that. So what I'm going to do now is just multiply across here, and we'll keep this 1 over just on the outside for now. So I've already done the calculations like ahead of time, but what this will be is I'll write them down anyway, just so it makes it clear. So I'm just going to do this symbol here just to represent this again, just so I've got more room. In the brackets now, so it's going to be 0.82 times this, and then minus 0.15 times this. So 0.82 times 15,360 minus 0.15 times 43,008. Okay, and then again, let's work out the bottom element of this matrix. Minus 0.08 times this, and then A times this. $15,360 again, and then plus 43,008 lots of A. Now we know this here now, this is the total population, and we've been told that the total number of chimpanzees was 64,000. So 1 over 0.82A minus 0.012 times this should be equal to 64,000. So if I just simplify this and then write my 1 over again, so what this is equal to is 1 over 0.82A minus 0.012 times, so 6,144, and then minus, in fact I'll do the positive first, so 43,008 A minus 1,228.8. This is equal to 64,000. Okay, so this is equal to 64,000 because that's the total population, right? So, but we just said that these two added together again is the total population. So, because obviously the juveniles and the adults must be added together to give the total number of chimpanzees. So we can rewrite this again as 1 over. So this is going to get quite tedious. It is quite a long question. 82A minus 0.012. Adding these together now, what I'm going to get is 4,915.2 plus 43,008A. This is equal to 64,000. So now this just has to be solved. So what I can do is I can times both sides by 0.82A minus 0.012. So what I'm going to do is I'm just going to clear everything here and then start multiplying through. So multiplying through, well, the left hand side would just cancel. I'd get 4,915.2 plus 43,008A. This will be equal now to the right hand side times by that bracket. So I'm probably just going to run out of room again. This is quite a long question. So it's going to be 64,000. I'll just do it in black just so you can see on the white part here. So it's going to be 64,000 times 0.82A minus 0.012. Okay, so I've got to do 64,000 and then expand this bracket here. So I'll just move this across a bit more. Hopefully I'll have enough room. So this side here will remain the same, 4,915.2. So just rewriting that side again. This side now, if you expand this through, what you'll get is 52,488. And you'll also get minus 768. Okay. Now we've just got to solve this equation in terms of A. So really easy. So solving this now, I'm going to get 9,472 A is equal to 5,683, sorry, 0.2, and then therefore A must be equal to 5,683.2 divided by 9,472, giving us 0.6. Okay. So there's our value for A. Okay. So we've still got quite a bit of this question to go yet. We now have to calculate the change in the model of in the number of juvenile chimpanzees in the first year of the study using this model. So this is B part 3. Well, in our model, for the juveniles, we had 1 over the determinant times 6,144. So that was the juveniles. And then the adults was the 43,008 A minus 1,228.8. Okay, so my juveniles is this number here. This is the key number. So I'm going to do 6,144 divided by the determinant. So I'm doing 1 over the determinant times this, or basically this number divided by the determinant. And what this will give me is this will give me the previous number. And then using that number, we can just work out the change in the number of juvenile chimps. So this will be 0.82. So it was 0.82A, so that's 0.6 for A, because that's what we worked out here, minus 0.012. Okay, put this on your calculator. What you'll get is 6,144 divided by 0.48. And if you put that in on your calculator, what you get is 12,800. So there were 12,800 chimps. So we started with 12,800. The next year there was 15,360. So how do we work out the increase? Oh, we're just going to subtract them, right? Nice and easy. Do this on your calculator, and what you'll get is 2,560 chimps. So that's the increase. So that's my increase. Okay. Part C asks us to comment on the short-term suitability of this model. Well, it does say that the number of juvenile chimpanzees is known to be in decline in this country, but our model has just shown an increase to 2,560. So what we can say is that the model is not suitable as the model has an increase. Okay, so that's part C. So it's just a brief 1 mark comment, and because ours is increasing, whereas it's known to be decreasing, they're in decline, then we can say it's not suitable for the short term. Okay, so if we just clear that, and then finally for part D, 2 marks, we're asked to refine the matrix system for the model to reflect this information. And what we're told is that the study of the population revealed that adult chimpanzees stopped reproducing at the age of 40 years. So if they stopped reproducing it after 40, what we could do is introduce a new, we almost call it a variable, right? So what we had was we had juveniles, we had adults. I'm going to introduce a third one now. So if we call them, say, elderly or mature, we'll call them mature. So okay, so mature chimps. Okay. So if we call this M, N, and what we're going to do now is represent this as a 3 by 3 matrix here. So it's not 2 by 2 now, it's going to be 3 by 3. And it won't be Jn plus 1 and An plus 1, it'll be Jn plus 1, An plus 1, and Mn plus 1. Okay? And where it's Jn and An, we've got an Mn here. So we can represent this now. So if I do it down here, so I've got extra room. So it'll be J, M plus 1, A, M plus 1, and then M, M plus 1. This is equal to a 3 by 3 matrix now. So this 3 by 3 matrix, for the values, you can put pretty much anything in because you're just representing what this system could be, this model, right? But there's a few zeros that need to go in. And you need to think about what you're multiplying it by. So it's going to multiply similar to how it did here. So it'll be Jn, An, and Mn. Now, the key thing to think about is obviously the fact that a juvenile chimp can't go from juvenile to mature. It clearly can't skip that middle life stage. And similarly, a mature chimp can't regress to a juvenile chimp. So we're going to need some zeros in, so that once we perform the multiplication, those two ideas aren't possible, okay? So if I say that's A, that's B, if I put a 0 in here now, what that'll happen is when I multiply this row with this column, I'd get an A lot of JN, a B lot of AN, and 0 lots of MN. So what we're saying is that the juveniles cannot just go, they can't go from juvenile to a mature. So that's good. Doing the same here now, we'll get a C, we'll get a D, and we'll get a 0. And same again here now, we can't go from mature to juvenile, so that has to be a 0 as well. And then this can just be E and F. So my A, B, C, D, E, and F, they're just representing a value. That's not important, but the idea that these zeros here and here and here are important. It's illustrating the fact that a juvenile chimp can't become a mature and vice versa. A mature chimp can't become a juvenile chimp. But there we have it. So that's question 10 fully complete, and that finishes the core pure paper. If you're new around here, guys, be sure to subscribe. I'm going through all the 2019 further maths papers.